This is section 4, rate of change, example 5. So before I get into example 5, I want to look at some real-world situation, right? Applying what we just did. So this is how you'd see it used in real life, okay? Because, of course, nothing we ever do in math doesn't have an application. This is the application. So suppose that an object is traveling along a straight line according to the formula S of t equals 2t plus 3, where t is measured in seconds and S of t is measured in feet. If we went to complete the table, it's actually really easy because it's all linear, right? So if I plug in 0 for t, I get 3. And then by plugging in a number for t, it's going up by 2 each time. So it's 3, 5, 7, 9, 11, 13. Okay, and it could keep going forever. To calculate average velocity between t equals 0 and t equals 4, we know that average velocity is the total distance over the total time. So the average velocity would be whatever the total distance was, so 11 minus 3, which is 8, over the total time between 1 and 4, 0 and 4 was 4 seconds. So 8 over 4 is 2. Okay, and then because we were doing distance over time, it's the distance unit over the time unit. So because distance is measured in feet and time is measured in seconds, it would be feet per second. If I wanted to know the instantaneous rate of change, which is what we were talking about when we were talking about instantaneous rate of change, instantaneous velocity, which is exactly how fast we were traveling at a particular moment in time, the only way to do that would be to use the slope of the tangent line formula that we used before, okay? Because you can't find the total, you can't find the velocity using total distance over total time because that total time would go towards 0. Right, because we want the instantaneous rate of change, which is not an average rate of change over time. It's the rate of change at a particular moment in time. So, in this box, there are some formulas that you need to know, but I don't want you to memorize these because you already know that average, or the average velocity, which is the same thing as the average rate of change, is just the slope of the secant line. And you know the instantaneous velocity is the formula, which is the limit as f of x plus h minus f of x all over h, right, as h goes to 0. So you see these formulas that are here, right, they're just meant to confuse with the different letters, all right, because if I write the formula that you know, f of x2 minus f of x1 over x2 minus x1, the f and the s are interchanged, and the x and the t are interchanged. So don't get confused by different letters. The formula hasn't changed. The formula is exactly the same. The same for the instantaneous velocity. We're trying to find the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, again, the f and the s are interchangeable, and the x and the t are interchangeable. And in the other formula that you saw, it was x1 for both of them instead of t1, or instead of just x, okay? So don't get bogged down by the formulas. Just remember, the instantaneous velocity is the same thing as finding the instantaneous rate of change, okay? Because velocity is that rate of change that we're worried about. So now I'm going to do the example. Right, it's just a real-world application. If S of t equals 3t plus 1 is a measure of feet traveled with t measured in seconds, find the average velocity and the instantaneous velocity. Notice this time it doesn't ask for the equation of the tangent line, but it would be very easy to just come up with it on the spot, okay, after finding these two things. So, to find the average velocity, we would find S of 3 minus S of 0 over 3 minus 0, or f of 3 minus f of 0 over 3 minus 0. I'm using s because our function is named s. That's all. We plug it in, so we get 3 times 3 plus 1 minus 3 times 0 plus 1 all over 3. Well, 3 times 3 is 9 plus 1 is 10 minus 1 over 3, which is 9 over 3, which is just 3, right? Pretty simple. For the instantaneous velocity, we're going to use our limit formula. So the limit, as h approaches 0, of f of x plus h minus f of x all over h. We get the limit as h approaches 0 of f of 2 plus h, because we want to find the instantaneous velocity at 2. Right? Always write down all the equations if possible. So we get the limit as h approaches 0. We're plugging in 2 plus h into, what is the equation? 3t plus 1. So we'll have 3 times 2 plus h plus 1 minus 3 times 2 plus 1 all over h, and we'll do the math. So we distribute first. We have the limit as h approaches 0 of 6 plus 3h plus 1. 3 times 2 is 6 plus 1 is 7, so we minus 7 over h. Again, all those numbers cancel out, which is very nice, which means that we're just finding the limit as h approaches 0 of 3h over h. Those cancel. If I plug in 0 and there's no h to plug it into, the answer is just 3. Now, keep in mind, right, the answers, they both happen to be 3. It happens because it's linear, right? That doesn't always happen, and you'll see that in the next problem. But don't forget units. It says it's a measure of feet traveled with t measured in seconds, so it's going to be feet per second for both of these.